This is EE 435, Communication Theory 1. As I said in the introduction, we start by talking about analog modulation techniques, modulation and demodulation techniques in this course. Okay, so the first chapter is about amplitude modulation. Now, what is modulation? I'm sure many of you have an idea, and feel free to stop and ask and interact with me at any time, because that makes the class more interesting when people ask questions or raise comments. Modulation is essentially taking a signal and changing certain properties of it so that we can transmit it. In modulation in the sense we understand in communications. Of course, there's modulation in other areas, such as in music. You take a signal, you embed it into another signal to change the properties, to create a different sound, for example. In communication, most of the time, modulation is used to take a baseband signal, which is at low frequencies, and put it in a high frequency band, which is suitable to the transmission medium and to the transmission band that we're allocated. Okay, so in this example, you see a message signal. One moment. M of t. I'm supposed to be able to mark. Okay, M of t is the message signal here. Suppose this is an analog waveform that we would like to transmit. It could be a voice recording, for example. Okay, and this is what you see below is the carrier waveform. As you can see, the carrier is a sinusoid at much higher frequency compared to the message. You can see that the message is changing slowly, and the carrier wave is oscillating very fast. FC here is called the carrier frequency. Now, why do we call it a carrier? Because it's going to carry the message signal. Specifically, we want, in this case, to modulate the amplitude of the carrier with the message signal, so that the amplitude of the carrier will contain information about the message signal now. The way we do it, essentially in amplitude modulation, is to multiply the message and the carrier, which we call mixing in communication. Now, why do we modulate in communications? There are various reasons. First of all, by using multiple carriers, multiple carrier frequencies, you can put different messages at non-overlapping spectral bands and send them all at the same time. Think about it. You have an M of t here. If you had another signal, let's see, if you had another signal like this, suppose this is N of t, this is another message. If you wanted to transmit them at the same time, you cannot simply add them, right? Because they would get confused with each other. When you add them, there would be loss of information. However, we will show that if you use different carrier frequencies, for example, use FC1 for this one and use FC2 for the other one. If FC1 and FC2 are sufficiently distant from each other, the two messages will be modulated and sent together, and we will be able to decode them separately. There will be no loss of information. Okay, and we will definitely be seeing mathematically how to do this in a few minutes. Another reason that we modulate up to higher frequencies is that the higher the frequency, the smaller the devices you need, such as antennas and other components. You know this from electromagnetics theory. Because the higher the frequency, the lower the wavelength. The lower the wavelength, the smaller the antenna, etc. Okay. There are other reasons, like propagation, for example. Higher frequencies have different modulation propagation properties than lower frequencies, but that is sort of beyond our scope at the moment. Another reason we modulate is we want to be immune to noise. We will not see this noise immunity issue too much in amplitude modulation, but when we go to phase modulation techniques, you will see it more emphasized. Okay, now the message signal, like the M of T that we saw in the previous slide, is often thought of as a baseband waveform, meaning something centered around 0. Okay, usually a power signal as opposed to an energy signal, meaning doesn't have finite energy, so it's a continuous waveform with a certain power. At first, we will think of it as a deterministic real valued signal. You may think, well, if something is deterministic, then why send it even? Why communicate? Because if it is deterministic, it's essentially known. And you would be very right in raising this comment. And in fact, later on in the course, we will think of our message signal as a stochastic process. And in fact, that is why you took you took the course EE 306 in our curriculum, which is called stochastic signal process. That is the whole reason you took that course, because we will be dealing with stochastic signals in this course. As you know very well, when we have a stochastic signal, or statistical signal processing, maybe it's not stochastic, it's usually the same thing. When we have a random waveform or a stochastic process, we often characterize it with its spectral properties. If it's a wide sense stationary process, we characterize it with a power spectral density. Okay, and later on, instead of the message spectrum itself, we will be dealing with the power spectral density of the message. But at the moment, we are considering real message signals for simplicity. So our real message signal, deterministic and real message signal will have a Fourier transform that is symmetric, whose real part has even symmetry and whose phase has odd symmetry, right? So this is a typical message signal. Any questions so far? Okay, so let's move on. Now, the first type of amplitude modulation we will study is called double sideband suppressed carrier, abbreviated as DSB-SC. Now, DSB-SC is the simplest thing you can do, essentially. Take the message signal and multiply it with a carrier signal produced by a clock generator at the transmitter. And this is the modulated waveform. AC here stands for the carrier amplitude. Later on, this AC will come into the picture when we compute the power efficiency and the signal to noise ratio of the modulation scheme. Okay, so AC times M of t times cosine 2 pi FCT. Since all of you know trigonometry, the rest is going to be quite clear to you what's going on. First, though, rather than using trigonometry, let's analyze this in the frequency domain. Okay. Now, this is our modulated waveform in time domain. In frequency domain, the multiplication will correspond to a convolution. So take the Fourier transform of the message and convolve it with the Fourier transform of the cosine, which, as you know very well, it is composed of two Dirac delta functions placed at positive and negative FC. Okay, and the result, of course, convolution with an impulse is a shift. Therefore, we have M of F minus FC times AC over 2 plus AC over 2 M of F plus FC. So we have a copy of the message shifted to the right and to the left, of course, appropriately scaled. Now let's see this a little bit better. Let's take a look at, in fact, let's take a look at the amplitude and the phase separately and to see what's going on in terms of the information content when we do this shift operation. This triangle represents the magnitude. Oops, what happened? Sorry, I skipped all the way to the end. This triangle represents when you look at the modulated waveform in spectral domain, you see the triangle which represents the message amplitude spectrum shifted to the right and to the left. It's centered here around FC and centered here around negative FC. Now focus on the blue part and the red part. You see that the blue part, this blue part has come here. This red part is to the below FC, but there's another red part below negative FC. Now, in principle, if we only got this blue part and this red part, we would be having enough information to reconstruct the original signal. This is a visual argument. It is not a mathematical argument, but later on we will make a mathematical argument for it. I'm just making a sort of a sneak preview into single sideband modulation. However, we are going to ignore the fact that only the upper sideband contains enough information and the lower sideband also contains the same information. We'll ignore this in double sideband and transmit both sidebands together. That's why it's called double sideband. So the double sideband, I don't know why I'm getting the eraser. So if somebody solves this, please tell me. Double sideband stands for transmitting both the upper sideband, which is outside of FC and negative FC, and the lower sideband, which is the region between negative FC to FC together. So we are essentially repeating information when we transmit this signal U of t. Okay, so we're using essentially more bandwidth than we need. Okay, and some of you may be thinking, okay, the modulation type is called double sideband suppressed carrier. What does suppressed carrier stand for? Any ideas?
The carrier itself is not transmitted with the original signal.
Exactly. You will later see that in conventional, I mean, today, in fact, we'll see that in conventional amplitude modulation, we also transmit the carrier, which helps in demodulation, okay? But in double sideband suppressed carrier, we're not sending the carrier together with the signal. I mean, the carrier is used only for modulation. Okay, so what is the transmission bandwidth? If the original signal has bandwidth 2W, okay, I mean, or you may call it W, only referring to the positive part, the transmission bandwidth for the modulated waveform is 2W. But as I said, we're using twice the bandwidth than we need, which we see by this visual argument. Okay, now to understand the math a little bit better, let's start by a very simple message signal, which is a single tone. Single tone means, as you know from signal processing, it is a cosine or a sine. It's a cosinusoid. Okay, it's a sinusoid with any arbitrary phase. A sinusoid with any arbitrary phase will have exactly this kind of magnitude spectrum, which is a single impulse. Okay, in time domain, our carrier is also a sinusoid, so it's another impulse at higher frequency. Okay, so when we modulate, what are we doing? We're taking this impulse and putting it around FC. Okay, the result is something that looks like this. Okay, so of course you need to take into account that the magnitudes are also multiplied. Why do we have this 4? Because we have the 1/2 that comes from the expansion of the sine, I mean, the Fourier transform of a sinusoid has 1/2 delta f minus fc, etc. So 1/2 comes from this one, 1/2 comes from this one, and then as a result we have 1/4. All right, look at how the result is looking. So we have an inner oscillation caused by the carrier, and now we have the amplitude of that modulated. Interesting. So how are we going to extract this information about the message signal from the amplitude variation? That is called demodulation. And we'll see techniques for it. First, let's talk a little bit about how DSB-SC is generated. An analog multiplier is called, that we use, what we refer to as a mixer. Okay, a mixer. And there are many different possible circuit topologies for a mixer, each with their own merits and downsides. We will consider these merits and downsides a little bit when we come to more advanced chapters throughout this course. However, they will never be our focus because they are studied in RF electronics, which is outside the focus of this course. Those of you who are interested, I recommend you read on those or take a class on those. There are lots of issues regarding the design of mixers and other components that in return affect communication system design, because they're going to affect power efficiency. They're going to affect, for example, local oscillator leakage is a phenomenon that causes spurious messages in a demodulator that we need to be careful about. Later on, you will understand these things more broadly. Another idea, rather than using a direct mixer, is a switching modulator, which is a circuit that is composed of this bank of diodes, which serves to allow the message signal to be periodically on or off when we feed the circuit with such a square wave. The result, you may say, okay, how is this double sideband suppressed carrier? Just when you look at this, does any of you have an idea what this has to do with modulation? Basically, M of t is essentially multiplied by the square wave rather than a sinusoid. How does this, how may this be equivalent to modulation that we saw earlier? Okay, remember your Fourier series expansions, and you'll realize that a square wave is made up of sinusoids, right? So when you, if you can think of this as a Fourier series expansion, or you can see this as a Taylor series expansion, like in this case. When you expand this square wave in a Taylor series, you'll see that there's, in this case, there's a DC term plus the first harmonic, which is at WC, the third harmonic, etc. Only the odd harmonics are appearing here. And obviously then when you multiply M of t with this W of t, we have M of t itself plus M of t multiplied by cosine WCT, which is the double sideband suppressed carrier that we want, plus higher order frequency components. What can we do to eliminate the higher order frequency components? Well, we could use a bandpass filter. A bandpass filter centered around what?
Carrier frequency.
Right, the carrier frequency, WC. Why is it bandpass and not a low pass filter?
Carrier frequency is much higher than baseband, so it's not a low pass filter.
Well, we could use a low pass filter, but then we would be also letting M of t come in, I mean, past the filter, and we don't want that because our double sideband suppressed carrier is not in that form. Okay, so if you use a bandpass filter simply centered around WC, which is 2 pi FC, the result, theoretically speaking, if everything works perfectly in an idealized way, it is equivalent to double sideband suppressed carrier. For this to work, of course, FC has to be bigger than 2W. Why?
Aliasing olmaması için değil mi hocam?
This is not aliasing really. It's this. Okay, so but it is related, of course. So our signal is here. Again, the eraser. I don't understand why I'm getting the eraser all the time. So our signal, our message signal spectrum is here. And this is W. And when we filter, I have to take care of this problem. I have to somehow understand why. You see, I'm still getting the eraser. Okay, so this is here. Okay, now this is this part, this point is FC minus W. We do not want FC minus W to be crossing W, because otherwise, if W if FC was less than 2W, we would have these things adding up, which would cause loss of information. Okay, so this is the requirement for double sideband suppressed carrier to work. This is the requirement on how big the minimum carrier frequency can be. So that was modulation. Let's talk about how we recover the original signal back. In other words, how do we demodulate? Now, there's a received signal coming to the receiver. The received signal can be different from the transmitted signal in general. In practice, it's always going to be different from the transmitted signal because it is going through some medium which has its own filtering and other issues, right? But suppose for now, the received signal is identical to the transmitted signal S of t. For now. Now, the most common way of demodulating double sideband is you somehow produce the carrier frequency at the receiver. So here include cosine 2 pi fct, mix it with the received signal, low pass filter it, and you get your result. Now, first, let's see mathematically why this works. This is our, as I said, assumed for now that the received signal is the same as the transmitted signal. And this is the carrier from the local oscillator. Assume for now that it has perfect frequency at FC. Okay, and there's no frequency offset, that is. And when we multiply and low pass filter it, let's see what happens. We're going to use, maybe we can just write out the results. S of t is AC M of t cosine 2 pi fct. And here I have AC AC cosine 2 pi FCT. Now, what is cosine times cosine? Wow.
Cosine square, which is cosine 2, which is cosine 2 omega CT plus 1 over 2.
Very nice, very nice. So we have done AC. I cannot write with the eraser. Please don't give me the eraser. So you said 1 plus cosine 4 pi FCT, right, over 2. So that's what we have as a result of the mixer. Now pass this through the low pass filter. As you see, this is a very high frequency signal. It's not going to go through the low pass filter. So after the low pass filter, we're going to have, please, AC squared over 2 M of T. Cool. So the demodulation works. Another way of seeing this would be seeing what happens in the frequency domain. So the incoming signal is in this form, minus FC, FC. And when we mix it, what happens is, let me draw over here, we translated the whole thing to FC and minus FC. Okay, so this is, so basically we have a copy at 2FC and we have a copy at, oh no, 0, and we'll have a copy at minus FC and we'll have another copy at 0. Okay, so we have a double component at 0, and we're low pass filtering this one. Okay, I invite you to do this mathematically, write this out mathematically in the frequency domain. I only sketched it. Okay, now the low pass, we use an ideal low pass filter, but we don't need an ideal low pass filter, provided that this edge, this band edge here, is sufficiently far from this edge. If I can make my, I'm sorry, there is a, it's not always easy to get this marker. Okay, so if there is enough space here, then the low pass filter does not have to be perfect. Okay, so I invite you to work it out on your own and show the demodulation in time domain again. Now, what happens if we had an offset at the local oscillator frequency so that it's a little bit off, plus there's a phase? Of course, there's always going to be a phase difference, right? At least, but sometimes we have a carrier frequency offset as well. And this is a major, one of the major issues in actual communication systems. What happens in this case? So, in fact, okay, so now we're multiplying cosines of two different frequencies. What is the result? Cosine this plus this, right? Plus sine this minus this. Okay, so what happens as a result?
Sinyalimiz hala biraz modüle kalmış oluyor aslında delta F kadar.
Right. So let's work this out. Let's work this out. M of t cosine 2 pi f ct times cosine 2 pi fc plus delta f t plus theta. What is the expansion? Cosine of
Ezbere bilmiyorum hocam ben bunu ama toplamıydı herhalde cosine olan.
so cosine A times cosine B. Well, cosine A plus B is cosine A cosine B.
Minus sine A sine B.
Sine A sine B, right? From that, you can derive that this is, let's see,
Ha, sağ.
sine, oops. Cosine of 4 pi fc plus delta f t plus theta. Okay. Plus cosine 2 pi delta f t plus theta. Okay. Now, after the low pass filter, this component is going to be filtered out, and we have this remaining. So it is the message signal sort of modulated by annoying, very low frequency components. If this was voice transmission, if M of t was voice and we're listening to the output, this would be annoying. The delta F modulation would be annoying. On the other hand, the human ear is insensitive. Well, I can't say this for everyone, but the average human ear is insensitive to phase differences. So for most people, the phase difference will be unnoticeable. Okay. So this is some kind of distortion. We will see other kinds of distortion in communication systems. So that essentially brings us to the end of today. Next time, we'll take it from here and talk about carrier recovery in the demodulation of amplitude modulation.